name is Zong-Han Xie, and I was worked for an LCD panel maker called INNOLUX. 中文名称叫群创. I think you know. Because I worked in the R&D department, I studied the optics for the LCD device roughly 4 years. Yeah, and in company, in manufacture, the environment has many restrictions. So I decided to write another open source program so that I can do the kind of research that I want to do. And today I'm going to talk about my program. So I'm going to introduce the physics that involved in the LCD device first, and the model I used to model in LCD device, and my program. I will simply introduce my. I will briefly introduce the structure of my program, and then I will give some demos. Okay, LCD device is I think everybody knows because everybody has many consumer electronics. They are all if they need a display, most of them is LCD. Like your TV or your cell phones, these are two most major consumer electronics. LCD device is different from the LED because LCD device is simply just the optical switch. It needs a light source, and the LCD layer, the LC layer, liquid crystal layer, is used to control how much light can propagate through this pixel. And use this device, so and the RGB pixel, they control the brightness of these RGB pixels, so you can have the pictures or the screen or your screens. You can have your images on your screen. Okay. If in this picture, your light source is on top of this picture, and simply speaking, that it is the light goes through a polarizer. It polarizes your light. In your light source, the light is unpolarized, and go through a polarizer. The light becomes maybe linear polarized. And we use this ITO film. These two ITO film. They are conducting materials. So we can add some voltages on these two ITO film. Voltages between these two ITO films. And with this electric field, you can control the orientations of the liquid crystal. And this orientation film, normally in the company, we call it alignment film. This is composited by the polyimide. It is used to fix the liquid crystal molecular orientation on the boundary. So so that your liquid crystal molecules in this layer will oriented in certain order. If you are, I don't know how many of you are physics background. This is I'll simply introduce that the light is an electromagnetic wave, and the electric field is a vector field. So there's a polarization. There's a polarization of the field. The polarization means the direction of your electric field, and how it changes with time. For example, in the first picture, the electric field, because it's a vector field, so you can separate them in two components, two perpendicular components. And when the light propagates along this direction, you can see the electric field, it oscillates along this line. And in the second picture, the electric field, the direction of the electric field, it rotates, just like it rotates like a circle. This is called circular polarization, and this is called linear polarization. And the situations in between is called elliptical polarization. it could be an it could be an ellipsoid. Looks like an ellipsoid and in many directions. This is a basic property of light. And I want to talk about another property called birefringence. This is a calcite crystal. The special of this crystal is that if you put it on a paper or a book, you will see two images. Two images because this crystal, if you use a glass, it will refract the light. But in this crystal, it refracts the light in two directions because it has two different refractive index. This is this is called birefringence. The light incident into this crystal will see two refractive index, and they will have two different directions to refract. This is the picture I drew to explain the last picture. This is a light that incident into the crystal, and because of this, the crystal is on this side, and it has two refractive index. Is NO. I call it NO and NE. So the light incident into this crystal, and there will be two refracted ray. This is the reflected light. Another important feature for the birefringence, and this is the most important feature used in the liquid crystal device, is that you have two refractive index. It means you have two light speed. You can see that if this light comes from this direction, comes into this material from this direction, it is initially a linear polarized light in this direction, along this direction, and the electric field was decomposed to these two components, but they have different refractive index, so they propagate with different speed. So it's linearly polarized, and while it propagates through this material, through this maybe crystal, the phase difference, the difference between these two polarization, you can see that this is the 0 point is together. The phase, the difference of this between this blue one and this green one is the phase difference. Okay, the phase difference is gradually changed when they are passing through this crystal. So when the light propagates through this crystal, it becomes another linear polarization light along this direction. So if you change the thickness, or you can change the refractive index of this crystal, you can get other polarization, other kind of polarization, the light with other kind of polarization when it propagates through this crystal. In liquid crystal, I assume this is a liquid crystal or liquid crystal molecular. So this is the optical axis. The black arrow is the optical axis of this liquid crystal, and the red one is the direction that the light propagates. And if you are not propagating along this axis or a direction perpendicular to this axis, you will get two refractive index. One of them is always NO. The other one depends on the incident angle. The angle that the light propagates, and between the light propagates and the optical axis of the liquid crystal. And you can modify the refractive index through by changing the direction of the light in the incident light direction, or change the direction of the liquid crystal. And we know that the direction of the liquid crystal can be changed through electric field, because if you are not applying any electric field to this this liquid crystal layer, the liquid crystal will orientate in the same direction, and the boundary, the most the liquid crystal molecule most close to the which is the most close to the boundary will be will interact with the alignment film, and the alignment film will orientate that molecule in certain direction, and on this side is the same. And due to the force between the between these molecules, they are oriented in the same direction. But when you apply an electric field, these two boundary conditions are the same, but in the middle they are starting to change their directions to align with the electric field. And because you can change the direction of the liquid crystal molecule, you can change the refractive index that the light sees when it propagates through this liquid crystal layer. So in order to model such a system, I need to, it includes two parts of the calculation. The first one is to model. I have to calculate orientations of the liquid crystals in the liquid crystal layers. When I have the liquid crystal orientations, I can use these. If I know all the orientations of the liquid crystal molecules, I can calculate the polarization, the change of the polarization when the light propagates through the liquid crystal layer. So it includes two parts of the calculation. The first part is to get the liquid crystal distribution, and the second part is to calculate the optical effect that caused by this liquid crystal distribution. And my program is now only has 1D model, one-dimensional model, and this is a simple diagram that explains the model, the imaginary structure that I put in my program. Liquid crystal layer is here, and they are and it is sandwiched by two alignment layer. I call it CF and TFT. This is my old terms in the company. This TFT because this side it has TFT switch, and CF means color filter. The color filter that to make the pixel has color is on this side. So so this is, I call it CF alignment layer, and this is TFT alignment layer, and liquid crystal is sandwiched between them. And the coordinate system is like this. The light propagates through along z directions, and this side is always 0 volt. I set it as ground, and this side, the voltage I want to apply it on this liquid crystal cell is applied on this side. This is a free energy called Austin-Frank elastic free energy. This is to model I regard the liquid crystal layer as a continuing elastic material, and it can be deformed with certain directions. And this formula describes this formula gives you the free energy density for when the liquid crystal layer is deformed. You can, if you have the high school physics, you can see this is like a kx square. When you are deal with the 弹簧，忘记英文。Oh, spring. Okay, like when you are deal with the spring, but you are continuing elastic layer, so the deform is there are many directions. Okay. And these three terms, it includes three kinds of deform. And this Q0 term, sometimes we add some materials into this liquid crystal layer so that it has, we'll call it chiral. It has helicity. Yeah, and the strength of that property is described by this term. And this is the electric field energy density. This is when you are. This is total free energy density, and this term is when you are applied electric field on it, you will get this term. And this D is expressed as this. The epsilon is the dielectric tensor. It is important that here this is a dielectric tensor, not a dielectric constant, because this is an isotropic material. And it has distribution, because the liquid crystal orientation is different anywhere in this liquid crystal layer. So it's a non-isotropic and inhomogeneous material. In order to get the liquid crystal distribution, I have to, there are three constants here, and they are mapping to these three kinds of deformation. They are simply the elastic constant when you are doing these three kinds of deformation to this continuum elastic material. In order to get the liquid crystal distribution, I have to I get the liquid crystal distribution by minimize the free energy. And to minimize the free energy, I use Euler-Lagrange equation. The Euler-Lagrange equation is like this. It's a variational method, yeah. And actually, I just solve it iteratively until it converges. But this iterative process, I treat it like a pseudo-dynamic process. That this Ni means the direction of the direction of the liquid crystal molecular. Oh, okay. So its change is I use a viscosity. This viscosity is called rotational viscosity. This is the only one viscosity that the supplier can give us. It describes the viscosity, but when the liquid crystal molecule are starting to rotate.
So what's a pseudo-dynamic process?
It's not a real dynamic function because it has no physical meaning. Yeah, because this is a variation. This is a variation. This is a I call it Euler-Lagrange equation is a variational method. The point to do this is only to acquire the extremum value, yeah. But I treat it like a dynamic process, but it's not real. Although when I was working in the company, you can if I print out the I record and view the dynamical process that this equation gives me. It's qualitatively similar to actually seen in the experiment. Okay, but it's not true. Okay, so this is to get the minimum free energy, but I have to calculate the electric field in this term. The electric field is calculated through the Laplace equation, and it's different from the usual Laplace equation everybody solves because it's non-isotropic and inhomogeneous due to this term. Okay, and this term is a tensor looks like this. This theta and phi is local liquid crystal molecular orientation because you have the liquid crystal distribution, and you have two dielectric values. It's along the liquid crystal axis and perpendicular to the liquid crystal axis, and you have to do use Euler angle to do the coordinate transfer to the lab coordinates. Okay, so due to the liquid crystal distribution is different everywhere, so your epsilon tensor is different everywhere. With these two equations, this is the two equations I solved for in order to get a liquid crystal molecular or liquid crystal distribution of the liquid crystal moleculars. And now it turns to the optical calculation part. In maybe in general physics course, you get an optical calculation method called Jones matrix. But Jones matrix has disadvantages because it can only calculate the light normally incident into a material, because it doesn't consider some other fact like the Fresnel equation. The light will be refracted or reflected. This doesn't consider it in Jones matrix method. And in this program, I use a modified Jones matrix method. that can be used to calculate at least to calculate the brightness or the transition of the light polarization. In this method, I used an assumption that the two refractive index in the material are roughly the same. When they are roughly the same, you don't have two light. The lights incident into this material have only one propagation direction, so you only have to calculate the phase difference caused by this two refractive index. So this modified Jones matrix method looks like this. This is a Jones vector for the incident light, and when it propagates through an interface into this material, there will be some of the light will be refracted and reflected. There will be S wave and P wave, and they have different transmission rate. The transmission rate can be obtained from these Fresnel equations. And when it propagates into this material, I will do a coordinate transfer from S wave and the P wave coordinates to E wave and O wave. E wave and O wave is the eigenstate of when the light propagates in this birefringent material. When I do the coordinate transfer, then I calculate the phase difference. And then I do another coordinate transfer back to the S and the P coordinates. And then the light will incident into another material. You have another transmission rate on the second interface.
Why can you make the assumption of the two refraction index to be approximately the same? And if you don't make the assumption, what will happen?
Okay. I make this assumption because in liquid crystal, in LCD manufacture, the parameters of this material we get can use this assumption to do thing. Roughly the same means like the difference between these two value is less than an order. Yes, it's roughly like that. In the edge, it's like 1.5 and 1.6. So it's on the edge. The difference is on the edge of this approximation. If I don't make this approximation, then the light will propagate in two directions. And in this assumption, I just have to consider the phase difference. So I can literally track the polarization change of the light. But if I don't do that, there are two directions. And I have to solve the entire electromagnetic field. Yes, there are methods to do that, but I haven't implemented this yet. The reason to use this is because of this. Because the LCD manufacturer use the incoherent light source, and in this 2x2 method, it is easy to get the transmission rate in this method because it can be reduced to this form. But if you are using other method, another method called Berryman 4x4, when you are calculating the transmission rate, you will get many interference on the transmission rate, the transmission distribution along the angle, because it assumes that the light is in that method, it's hard to do the results for incoherent light. And this method is useful. Now, it's useful in to estimate the results we want to see. This is calculation for one wavelength. If you have if you want the transmission rate for many wavelengths, you have to do this integration. This is the transmission for a wavelength. This is the the power distribution of the light source, and this is the visual efficiency of the human eye, because human eye have different sensitivity to the light in different wavelength. So you do an average, you see the transmission rate for the white light. Okay, this is a simple diagram for my program now, presently. I separated these. This namespace LCD put all the common parts that I may use in further 2-dimensional, 3-dimensional simulation. The LCD optics put like a common part that I can use in 2-dimensional, 3-dimensional simulations too, but they are for the optical calculation, like to calculate the Jones matrix, the extended Jones matrix when the light propagates through a layer. And this LCD 1D include the finite-difference solver, because the finite-difference solver, the one-dimensional finite-difference solver is different from 2-dimensional, so they are only restricted to 1-dimensional. And there's a main function for extended Jones matrix. They combine all the compartment for one layer. Yeah. And finally, I have two main classes that user can just use their member function to set up some conditions and calculate and get the results. I use Python to export these two API to Python, so that I can use Python and calculate, and then return the results directly, and I can use matplotlib to plot the results. And the best thing to use Python is that I use Python in C++ because it automatically converts the data structure. If you input like a dictionary, or a dictionary of dictionary, or a dictionary of a list, it will, into a C++ program, it will automatically convert into a map of vector or map of map, something like this. So you don't have to care about these details. You don't have to write another interface for this kind of conversion. You just have to put Python. You just have to export the API interface into Python, and you input the parameters with Python's data structure. The Python will do the conversion for you. And the other way around is the same. Okay. So not enough time, so I just put the demo. Okay, these are some simple code. Oh, I haven't built it. Oh, the Python hasn't support C++11 well, so some of the C++11 feature you have to write the interface by yourself, like tuple. So I didn't export the C++ interface with Python. Oh. So the first demo is this is called VT curve. The VT curve is that when you are apply voltages, this pixel will be this axis is the transmission rate. When you apply voltages, the liquid crystal orientation changes and the phase radiation changes. So the pixel may be from bright to dark or from dark to bright. So I calculate this. Python 3. Python 3. Static. So. This is the picture I saw, and I can also view the liquid crystal orientation, the change of the liquid crystal orientation. Let's see when it has no voltages, not apply voltage yet. Oh, I have to manually adjust this. When I haven't applied voltages, the liquid crystal is they are all on this XY plane and they rotate 90 degrees. And when the liquid crystal is in this state, this pixel is it transmits light. Light can propagate through. And if this is for 5 volt. If I have applied voltages 5 volt on the liquid crystal layer, you can see the liquid crystal molecule in the middle, they raise up. They will align with the electric field. And since the time has not enough, so I just jumped to the last demo. In old days, we use a technology called TN for the liquid crystal display. And it has a serious problem that if you are looking at this screen in some other angle, not just looking at it directly, you will see very strange the image quality. This is because in this mode, the performance of the phase retardation with different angle, they are not very homogeneous. So you can, I just wrong it. Oh, whoops. iPhone 3. Oh, and this code has I parallelized this code, so it used OpenMP. So if you see, you have 8 processes here. Because it's in the binary level, so the GIL does not cause the problem. The last one. Okay, wait for it. 7 voltage. Okay. Okay. This one is the transmission rate. This graph is the transmission rate when you are looking at the screen with different angles. There's azimuthal angles and theta angle. You see that when the voltages are not applied on this cell, the transmission rate is it's kind of not homogeneous, but it just look like this. But when you are apply voltage on it, like eventually I apply 6 volt into this cell. This cell should go dark when you are looking at it directly. This point means that you are looking at the cell directly, and the transmission rate is 0. But when you are looking at another angle, it has the light propagates out. Yeah, because it's birefringence, and liquid crystal direction is fixed in this liquid crystal layer, but you are looking at a different angle. So you see different phase retardation. And in some other angle, the light will leak from this display, so you see very bad image quality in this operation mode. So this is my demo, and there are something else that I want to do. Okay, so these are things I haven't do in the company, so I can do it outside because I have many more tools here. Does anyone have any questions?
I think we don't have time for question now, but we will have a refreshment right now. So if you have any questions, you are very welcome to talk to speaker. So let's thank speakers.